Je suis dans les parents.
Hi, nice to meet you. Good baby cool. Everything. We both work on online, so.
Ça marche du coup je vois que ça saute un peu, mais.
J'ai un peu de ça va.
Ouais.
Mais là, il est sur on. On change de titre? Non?
Hey
Tu vois, ça s'est marché. Ah oui. Ouais, j'ai vu toi. Et t'as aussi un. Moi, c'est fini, je veux que je revienne. En tout cas, on va. Non, ça, non, je sais pas.
Ouais, mais là, tu
Des choses nerveuses.
oui, c'est ça, je vais pas.
Non, peut-être pas.
Et ce,
J'avais pas anticipé que quelqu'un serait détruit comme ça.
Je pense pas que ça va marcher.
Non, je suis là.
Ouais. Par contre, là, par contre, tu montes, hein, là, tu m'entends bien.
Tu l'as vu Princeton?
Ouais. Mais là, tu mets. Ouais, écoute, on va. Ensuite, pour.
Je peux plus rien dire.
Pas longtemps. Alors, je sais pas si YouTube est commencé, mais là, si tu commences, il est. Peut-être que t'es pas du tout Pierre-Yves Lagré.
Nice, Sébastien.
Nice, ça va mal se passer pour toi.
J'ai pas de chemise. On va lui mettre une chemise. Là, ça va?
Je pense que là, ça va. Ah oui, là, ça va. Là, tu vois bien. Et tu marches. On attend quelques minutes. Ouais, je sais plus pourquoi ça fait. Pourtant, ça fait rouge quand je. C'est marrant parce que. Il y a l'air d'avoir des petits et tout, et le retour. Oui, c'est moi qui fais ce truc. Oui, on est en ligne. Voilà. Ah oui, tata, ok. Tu le marches. Non, ça va. Ouais. Ok, bon, on va commencer. Je profite du micro de Pierre-Thomas pour que la rediff m'entende. Ben, d'abord, merci à Antoine d'assurer la rediffusion YouTube aujourd'hui. Et puis, voilà, merci. Et puis, bonjour à tous. On accueille aujourd'hui Pierre-Thomas Brun. Pierre-Thomas a fait ses études en France, mais il est parti faire son M2 en Angleterre. Et puis après, quand il a cherché une thèse, il a regardé sur le magnifique site de l'école doctorale, ED-SMAER, et il a trouvé une thèse à l'Institut d'Alembert. Il est venu travailler 3 ans ici avec Basile Odoli et Nel Rib. Et puis après, je pense que tu as fait ta thèse en 2012, et tu es parti en Suisse pour faire un postdoc, puis parti instructeur en traversant l'Atlantique au MIT pendant quelques années. Tu as pris une tenure track à Princeton, et là tu es de retour en Europe, to make Europe great again, en Flandre, à l'Université catholique de Louvain, on dit Leuven, c'est en Flandre, où tu es arrivé l'année dernière, je crois, et tu vas nous parler de construire avec des liquides, si on arrive à faire marcher.
Ça saute un peu.
Ça saute. Il faudrait trouver la télécommande.
Ça saute en fait.
C'est le fil qui est mal mis.
Non, je bougerai ça. Ok, en anglais, hein? In English, yes. No, goedemiddag. Okay, so what as Sebastian said, I did my PhD here, and what Sebastian doesn't know is the first day I arrived here, I did like everyone else, so I had trouble to open the doors, and then I see a guy running to me. I had never met him. Right? It was Basile, and of course between his office to the door, he already told me about Mathematica, discrete elastic rods, minimization and stuff. So I was completely lost. And then I went for a coffee with him, and I ran into Sebastian with a very calm voice, starting to explain a few things. And I said, okay, maybe there is a savior for me here. So I was a bit less stressed, and things went smoothly. Okay, so yeah, so before being in Leuven, I was in the US, in Princeton, and my lab was called liquid elasticity. And so today I will mostly talk about what I've done in the past, and I'll say a little bit what I will do in the future. So I did a bit of fluid mechanics and elasticity, always focusing on slender structures or thin things. So film droplets, I'll talk a lot about that, elastic rods and membranes, and with a passion for shape-changing structures like this inflatable. We also did some fluid structure interactions, unconventional, let's say. So this is a rubber balloon, facts, and we did also some multi-phase throws in deformable structures. I will not talk about that. Today I'll talk actually about this empty box here, which is the conduit that you can have between fluid mechanics and elasticity. And the way I want to introduce this idea is through a little bit of rheology. So this is the rheology of an elastomer that's cross-linking. You don't see the line very well, but the blue one basically is a loss modulus, so tells you how liquid is something. And the orange is the storage modulus, so tells you how elastic is something. So you see that at the beginning, blue is above orange, and so it's a log scale. So it's more viscous than elastic. And at the end, it's more elastic than viscous, right? So it's this famous polymer that everyone, or many people in this room know, is vinyl polysiloxane, right? And so you mix them, they cross-link, and you go from a honey-like structures to a rubber, right? In 10 minutes or so. Okay, of course, this solidification is something that's pretty common in nature. We have icicles, but also people do this in art, sculpture, for example. But it's also a central aspect of industry, right? So if you actually look around yourself, many things here were once liquid, right? So concretes, the glass, and so you use their malleable form, you constrain them in a way that they meet your desired ideal. And so what I propose today is to remove all constraints and to let things flow the way they want. And if you do that, I think my video has disappeared, doesn't matter, but you can have interesting results. So actually, I did my PhD on the coiling of viscous threads, and this is a viscous thread here. The only difference is that this is molten glass. And so when molten glass cools down, you have this nice structure. And so the idea is we will try and see how we can build materials by harnessing fluid flows and interfacial fluid. So why do we do that? So I think you have to live under a rock if you've never heard about mechanical metamaterial, especially here. So I will not spend too much time introducing this, but this is not just about mechanics. It's about many fields of science in acoustic, optics, and functional surfaces. There is this idea that if you have a structure, you can emulate a function, right? So it's also inspired by nature, if you want, but people are working on that quite a lot. One issue, essentially, is that the scale of these objects are typically small. And so by small, I mean, a few microns or tens of microns, maybe a few millimeters or centimeters. And we're saying, oh, okay, we're going to use this to build our next buildings, airplanes, textiles, and everything. It's not exactly clear how you can master the architecture of something at such a small scale and make it actually available and cheap for everyone to use to build, buildings, skyscrapers. Conversely, if you look around in nature, you go and walk on the beach, you will see very nicely and very similar patterns at very large scales, right? Those ones come for free. They come through natural processes. So, for example, the dewdrops here on the spider web, they come through some variation of the Rayleigh plateau instability, or else, these nice patterns on this type of ice creams. Right? And so, the thing I want to point out is that actually many of those processes, they're built by, or they can be built by mechanical instabilities. And the question that we're trying to understand is, can we harness these instabilities so as to actually build these materials, right? And so people from Geneta, they have done this for a long time. So this ice cream, there's just a nozzle here. The ice cream comes in excess onto a conveyor belt. It buckles, and the rest you eat. Okay? So you can harness essentially this buckling instability to fabricate structures. Okay, and so when I started some years ago, I made this roadmap basically and say, okay, we can go in Rayleigh plateau, Rayleigh Taylor, some other non-instability, and try to solidify these structures. Of course, those things are well known in Newtonian rheology. They're actually also known in more complex viscoelastic fluids, but people usually don't worry about the solidification of those things. So today I'll talk about too many things, I think, but I'll try to give you a bit of a potpourri, as you say in good English, so a good aperçu of many of those things, and I'll focus on one instability. So this is just an example. So here, what you see is a bath of oil, and so that's a top view of a bath. And what you're about to see is a needle that's dragged inside this bath, and we're extruding glycerol. Glycerol and oil are not miscible. Right? So we're drawing a line of immiscible fluid inside the bath. So without surprise, what happens is exactly what happens when you open the tap. It breaks to the Rayleigh plateau instability. Okay, and you have a collection of drops. What happens is that this, okay, so that's the side view essentially of the experiments. We move faster than we inject, and so we stretch the thread before it breaks. And what you know is that, okay, let's say that this is this stereotypical instability, so K squared minus K4. I have this dispersion relation. I expect that I will only observe the maximum of my dispersion relation as the mode that dominates, but the sad news for this case is that actually this instability is effective, and so you also drag essentially a lot of noise in your system, and so the droplet breakup is not perfectly regular. So what do you do when you fail? You repeat, right? So now we do the same thing, and instead of just the same first line, actually it's the same moving, but what happens is that we're going to print a second line next to the first one, and then a third, and then a fourth, and so on. And don't worry, I'll accelerate the movie, otherwise it's very boring. But you can start to see that things get better and better, and as you keep going, there is this emergence of something that appears to be very regular. If you look carefully, actually, it's not perfectly regular because of boundaries, but it's actually much better. So, for example, if you plot the drop radius, or if you colorize by the drop radius, you see that whatever defect you may have had at the beginning, after a few lines, these things are forgotten. And the reason for that, essentially, is that, well, you're taking instability and you're applying instability on top of an instability. And so the mechanism is this one. So we know that when we have an instability, basically we're having a growth of an exponential growth, sorry, of whatever we call epsilon, right? So when this is linear state analysis, we assume that this epsilon is small, but it's rarely specified what this epsilon is. And in this case, what happens is that when we're printing a line next to an existing line, the perturbations of this one, they actually are inherited from the previous one. So if you want, it's like if you were taking some sort of convolution of this perturbation by itself. So it gets more thick and more thick. Another way of looking at this is you realize that if you take any daughter drops, it always sits at the, not the middle, but it sits at some fraction of the distance between these two ones. So if I look at the distance between these two drops, I can argue that essentially this is some sort of algebraic average of the distance between the two mother drops. Right? And so essentially, initially, you have a noisy signal around the mean, and you're taking an average of this signal, and an average of this signal. If you take a random average of something that's oscillates, you know that you're going to smooth essentially to something which is flat. So you're converging to this mode. I spare you a lot of details, and I take a lot of shortcuts. But the one thing that we also know is that these things are sort of alive. So when you drag the next lines, the drop move back and forth. And so you can basically create all kinds of crystals that have the same wavelength, but that have a different phase, right? So like this, you can essentially, these two pictures, they have the same wavelength and then a different phase. And the other thing you can do is you can sort of force the system to have the same wavelength, although they have a different thread radius. And so as such, you can actually create populations where you have two drop sizes inside the same bath. What I didn't tell you is that actually I lied a little bit. The white stuff is not oil, it's actually liquid PDMS, which is basically oil for the time scale of the experiment. But eventually these things are curing, and so you form these elastic slabs with liquid inclusions, and then these ones that have nice properties for acoustics and stuff like that. That's why we were working on those. Okay, so that was the first story. I'll showcase another instability, mostly because we don't really understand it, but that has a similar type of features. So this is an FDM 3D printer, right? So you're printing just regular lines, and so 3 lines have been printed. And this printer, you're trying very hard to break it. And so by this, we're actually under extruding, right? So we're not providing enough material to build the wall, right? So there is a lack of material. And what we observe is this. So instead of having basically a thin thread that we're stretching, we see the occurrence of this type of instability where it does like a sort of a dotted line. And this is not very regular, but because we're close to the onset, but you can get much more regular structures. In this case, I don't know if I have the movie. I have the movie. So what happens here is that as you stretch the thread cools down very quickly. And as it cools down, it's impossible for the feed to arrive back to the thread. And so you're forming a drop that will eventually impinge on the previous generation. And so like this, you're building this type of memory. So in this case, unlike the previous one, there is, I think, there is a coupling between the flow and the curing, but we don't understand everything, so I will not say too much about that. Okay, I will still say one more thing, sorry, is that you can make towers. And if you make towers, you have basically, you don't have enough material, so instead of being able to make this nice cylinder, you're going to take the rope and you anticipate the formation of structures that look like this, and indeed that's the case. So all those prints are the same in that we're trying to form essentially a cylinder, but we don't provide enough material, and so we see the appearance of these nice structures. But this is merely advertising because we don't, like I said, don't understand everything in this program. Yes. Sorry? Axis? Yeah, no. This is just a set of pictures. Yeah. But you can find basically the less material you provide, the less corners you will have, right? So the more material you have, you're close to this. A few buckling-like modes. It's not buckling at all, but it looks like it's buckled. And actually, it's the same thing as the previous instability. And if you have less material, you're going to convert to something that looks like this, which is, I think, a different instability. And the less material you provide, you will get eventually to something that looks like this. So indeed, those ones have less material than those and less material than those. Okay, so I'll move to my second story, which is about the Rayleigh-Taylor instability. So the Rayleigh-Taylor instability, it's a story that actually started at EPFL, so a long time ago. That's what happens if you coat a flat substrate and you flip the substrate upside down, right? Or that can happen by accident if you apply too much paint on the roof, right? So this will destabilize and create drops. Or when you're cooking pasta, on the underside of the lid under which you're cooking pasta, you will see these instabilities forming, right? So this is a similar, you don't see it very well, but basically this is this polymer, this polyvinyl siloxane, and we have coated it on the underside, and now we form this nice network of droplets. In this case, so this is the viscosity of the polymer as a function of time. So basically this is more like a doomsday equation, right? So you have mu, which is mu zero, which is the initial viscosity, divided by something that goes to zero violently, and so at about 3,000 seconds. But for the time of the experiment, this is more or less constant viscosity. And then these droplets, this is a logline, right? So they have an exponential growth, and then when they're lacking material, they sort of saturate, and their size becomes constant over time, and eventually things are cured. And because they're cured, you can do things like inflating these things. Don't ask me why, but you can inflate them just to show that they're elastic. Okay, this was actually a very nice idealized view. The reality is that if you don't, even if you work very carefully, what you will obtain looks more like this, right? And so what do I mean by this is that there are big drops and there are small drops. Another way of looking at this is you can take a Voronoi tessellation of these drops, and so you see that drops basically have access to different volumes of material. And so, well, where you were expecting maybe a hexagonal lattice, you actually get something that's a little bit more messy. Okay? And again, that's the same idea as before. Essentially, this instability starts where the defects are. The defects are usually at the edge, so you propagate in waves in the form of rivulets. The rivulets grow, they break into drops, so there is a long and complex history. After the droplets are formed, they can now still talk to each other. They flow, they can merge, they can drip. So there is whole kinds of complicated stuff that happen. But what we discovered with Joel is basically that if we were to make little holes into the plates in which we're making these coatings, and by holes, I mean we actually laser impulse on the acrylic, so we make little dents, and we make these dents at a size that's about the size that we expect from the instability, right? So everything is in the about, right? So the distance between droplets is 2 pi square root 2 the capillary length, so 10 times the capillary length. And so if you respect that and you run the experiment again, then you get a very nice network of droplets, right? So you can have hexagonal, triangular lattice if you want, or square lattice. And in both cases, these drops, they have now the same size, right? So you can tame this instability by providing defects, if you want, in your initial condition, which will be amplified by the instability. So it's a bit like the first story I mentioned. Interestingly, you cannot push your luck too much, right? So if there is this mode, that's the expected mode. If you go too far, too small, or too big, then you're going to run into troubles. And this is about the same margin. So too small is about 40%, and too big is about 140%. Right? So, and the why we get this, for the 140%, it's more or less clear. You have like a period doubling instability. For the 40%, it's not really clear what's going on. Okay, but for what I just talked about before, it's nice, but it's also a bit of a fail, right? Because we were talking about, making instabilities for materials, and now we have scales that are about a few millimeters. So this is big. For anyone doing material science, they see millimeters, they're just freaking out, right? So how do we make things smaller? Well, I said that the distance between drops was basically driven by the capillary length, right? And the capillary length is square root of surface tension divided by density times gravity, right? So surface tension, especially under a square root, you cannot change too much. Density, it's already 1,000 to 1, so it's as good as it gets. And the only thing we can change is now the acceleration of, not gravity, but we can try to find another source of acceleration. And so in that case, we use centrifugal forces. So we coat the outside of a cylinder, And if you code the outside of the cylinder, the physics remains the same, but basically, the faster you rotate, the smaller the drops you will obtain. Okay, but again, the physics remains the same. So I go a little bit fast, but essentially you can change the acceleration by orders of magnitude, but and then you change the drop size by order of magnitude too. Unfortunately, there's a square root, so of course you work hard. Please wait to change something, and you get. Ah, the font moved maybe. No? Suspense. Yeah. And you get these drops that are essentially pendant drops, right? So we're all very familiar with these pendant drops, but just their scale is different. So you can play a game and build like a Frankenstein droplet where you patch things of very different scales, but that's the same. Interestingly, if you go, you could go much faster, but then that's also where centrifuge could be used for military applications. So that's usually a good place to stop. And I say you can go much faster because we're still at microns. People have done relay plateau to tens of nanometers, so there's no problem to go smaller. You don't run into van der Waals or anything like that for quite some time, right? Okay, but at this point there's still no effect of curing, and then someone else came into play, so Etienne Jean-Puyer, and with Etienne what we looked into is this idea, right? So now we rotate, we get these drops. But what we do is we go back to this plot I've shown you and these two curves, but at some point they cross. It's a little bit arbitrary, but this crossing point is called gelation point in rheology. And so what we say, okay, we're going to increase the rotation speed quite fast at this point in time. And so at this point in time, you have a viscosity which is of the order of tens of pascals. But then as you increase rapidly, something might happen. But the cross-linking continues, and eventually you get something which is an elastic material all the same. So first, when we increase, it's already a gooey substance, so it's not going to flow and make other droplets. It's actually going to stretch and create these like hair-like structures. And what else? Well, nothing, right? So really, because you create a new reference frame, or shape, which will cure. And so when you go back to zero, these guys, they stay, right? So you grow, you stretch them, they cure, you relax the speeds, and then they just stay the same. Okay, and so we want to understand how they're formed. So it's not very pleasant to watch a cylinder rotating. So this is a flattened cylinder, right? So this thing is this cylinder. And I'll show a movie which represents what happens when we increase the rotation speed. And at the same time, I show here some results of a quasi-static, so there's no dynamics simulation for a hyperelastic material. Okay, so I'll not show the movie now. Yeah, you have to stay here. Really. Ah, il va chercher un adaptateur. The movie is nice. I'll show you quickly. No. Take a quick break. It's okay. For me, it's good. Huh?
Could you, on the first experiment you showed, the drops were aligned on the left and not aligned on the right.
Yes.
Like
yeah. So that's the boundaries, right? Because the printer has to come and start to drag. So that's more like boundaries effect. Okay, so if we had a no, we have dislocation and defects, but in this case, that was not the case. Oh, it works perfect. Okay, so here goes the movie quickly, and so yeah, you see the acceleration and these droplets. They actually stretch and create these hair-like structures. Right? This is too busy, but so forget about. I think, yeah, forget about that. Just look at this one. So this is a drop. In the red dotted line that you barely see, it's actually the integration of pendant drop equation. So we have a pendant drop. And then as we increase the rotation speed, we're going to stretch this shape. And then we find eventually this thing. And so I superimpose here the results of these finite element simulations for a static problem. And so you see that essentially it works well. So that's my justification for why I don't want to worry about viscoelastic effects or anything dynamic. Okay, so you can plot essentially how much you're stretching as a function of a dimensionless parameter, which represents essentially the ratio between the acceleration you impose and the elastic resistance. And so you see that things collapse more or less. They don't perfectly collapse because basically you stretch more if you're bigger, right? No, actually you stretch more if you're smaller. Sorry, the blue ones, they stretch more than the yellow one. But if you forget about this and you can try to predict essentially more or less this trend, what you can do is say, okay, I have something which is a piece of rubber. I can write the energy by writing an elastic component and some sort of gravitational component. I minimize that and I find some ugly formula, but this ugly formula seems to work pretty well. And the nice thing about this is that if I have a theoretical expression, I can basically predict what happens to the distribution I had initially. So initially, I have a distribution of droplets, which we fitted with a log normal fit, but it's centered around 1, okay, as we expect. And as we increase the rotation speeds, we stretch this thing, and so we're going to flatten the distribution. And so initially, the model predicts the distribution pretty well. So this is for 14 times gravity. For 27 times gravity, it's not so good. And for 88 times gravity, the prediction and the experiments are quite different. And the reason is because the theory is for axisymmetric assumes axisymmetry, but actually when you go very fast, you're losing axisymmetry. And so this is a joke I make in every places, but here it's a bit irrelevant. It looks like the Eiffel Tower. Right? So you have this delamination thing, you have these feet that appear. Okay, so we were happy for a number of reasons, but in particular because we managed to make this high aspect ratio structure, which is suitable for some applications. However, what you want is high aspect ratio and high density. And here we're actually not accomplishing this because the density is inherited by the low acceleration case, so they're quite far. So we stretch them, but they're still quite far. So the question is, how can we make them tall and close? So tall and close, here they are. Now they're tall and close. So how do we do that? You realize by looking at this that there are two colors, blue and purple. And what happens is essentially that we're coating, turning, waiting, taking it back, coating again, turning, taking it back. So we apply 10 or 11 coatings. And this is with just the exertion of gravity. So initially, you have your drops here for one coating, so this sort of irregular distribution of drops. And in yellow, we color new drops. So initially, we were here, n equal 1. And so you see that you don't have that many drops compared to what you're supposed to have, which is this prediction from the stability analysis. And you're also, conversely, the wavelength, if you want, is quite high. So we're almost at 1.25 compared to the one we were supposed to have. And if you apply another coating, you see new drops appearing wherever there was too much space between already existing drops. And after 3 or 4 coatings, there is no more new drops that appear. And you're converging to something which is actually what is predicted by stability analysis. So you're quite far from linear problem, but the predictions, they actually work fairly well. Okay, so we were interested into understanding how tall these things were and how different they were from each other. So you can look at the mean height of those things. So they grow linearly with a number of coatings, and basically they grow with the capillary length. So every time you're applying a coating, you're adding a little bit of volume, which is, of course, scales with the capillary length. That's not very surprising. But what's a bit more surprising is this. So if you look at the experiment, it feels like it's quite uniform. If you plot the data, you see that the size of the error bar is increasing, right? But actually, as a human, we're not sensitive to the absolute size of the error bars. You're sensitive to the size of the error bar with respect to the size of the object itself, right? And so if you divide the size of the error bar by the size of the object, actually what you see is that the relative spread is decreasing. So they're sort of almost converging, but not quite, right? So there's always a difference between these hairs, but they're less and less different in some sense. Okay, so but what are those? So you can take one, you slice it in the middle, and so you see that we applied multiple coatings, and there's a number of things that you can observe. The first thing is that you sort of alternate big and drop, but big droplets and small droplets, but okay, there's no real, it's a bit of a chaotic process in this case. And however, on the edge of the drop, there is always a very thin and uniform film. So you're combining a thin film, which is quite uniform, to a pendant drop, which are not uniform. Okay, I don't know why I show that, but what you can do is you can take an average, if you want, of all these shapes. And if you take an average of all these shapes, you grow to something that looks a bit like a cone. And essentially, this is not a big surprise because you're stacking things that grow linearly with the number of coatings. And then you're adding a little bit of a thin film, which actually is also proportional to the capillary length. And so if you combine these two things, and I go a little bit fast and I'm a little bit casual, but you can prove that essentially you have a cone with a specific angle, and you can integrate this sort of stereotypical shape, and you find something that looks like that. So I've been hiding a few things under the carpet here, but I'll leave it like that for now. Okay, so we were asked by reviewer number 3, what could we do with these things? And so they're actually funny to touch. So I said, okay, let's see what happens when we touch them. So you have a carpet of hairs, and you're gonna come and you're gonna indent them with, in this case, a vertical plate, a horizontal plate, sorry. And so if you do that, I will skip that. What you see is this. So there is the force, and the force is increasing, and it's concave up, right? So it's increasing with the displacement. It's not very surprising. But what's more fun is this. The force actually is increasing for 2 reasons, right? So you have this bump, these fingers, and you're compressing them, right? So if you think about them as being elastica, actually they're sort of compressible elastica, so you compress them a little bit, and then they buckle. So it makes sense that you will increase the force initially. But the other thing that happens is that they don't have the same size, and so as you indent, you're making contact with more and more of those posts, right? And so you can plot the force as the number of contacts. So these are my hairs, and as they appear red, they're in contact with the plate. So the force is now increasing with the number of contacts. And what's interesting, at least for us and for reviewer 3, is that the force can be actually predicted by just counting how many of those hairs are in contact. Because I know their size, I know their distribution. So if I can count how many are in contact, I can tell you what the force is. So it's a minimal force sensor, so we say. Okay. So with this, that's my segue to my last story. And this is a story also about elasticity. There will be no more pattern from, or there will be no more instability. But we're going to look at a fairly simple experiment. So the experiment is the following. So this is a tube. And this tube is made by carving actually 2 half cylinders into 2 acrylic plates. So we have 2 acrylic plates, 2 half cylinders, you put them together, and that forms this thing. The black stuff are screws. But for the purpose of this presentation, this is essentially a tube that has a tortuous path. And so what I do, and I'll show the movie a couple of times, but I inject this elastomer that we've been talking about. And after I'm done injecting it, I actually push some air the other way around. So I play again, you will see the elastomer invading the space. And then as you push the air, you see a bubble moving quite quickly through this network. Okay, that's the end of the active part of the experiment. Then you wait for 10 minutes. And during the 10 minutes, 2 things will happen. Gravity points this way. So whatever you've been coating, your cylinder will drain. And then this thing will cure. And so once you're done, you can take it away. And you inflate it, because that's a balloon. So what you do with balloons, you inflate them. And you have something that looks like a gripper, a soft robotic gripper. Okay, so this is my cylinder. I push a bubble. I'm carving this cavity, a Brun-like flow. I have initially a cavity that sits in the middle, and as time passes, the fluid drains or the bubble rises, and then eventually I get something that looks like that, which is now elastic. And so if I inflate it, this will deform more than that because it's thinner. And so if you have this excess of length, you will actually move in one direction. Okay, and do that. All right, so classic problem in interfacial flow dynamics. I'm moving a meniscus inside a cavity. I balance viscous effects and capillary effects, and I find that the thickness should vary as the capillary number to the 2/3. In our case, the thickness is quite large compared to the radius, so you have a slight correction to this, but essentially you get this stuff. Actually, the reference is missing, but you get this low, and you can plot this essentially thickness as a function of the capillary number, and so you see that you will get to a plateau. Yeah, that's sort of important. So if you push fast enough, essentially whatever was a 2/3 is more or less something that's flat. And so essentially, as long as you push fast enough, you get basically 30% of your radius as your initial thickness. So that's the initial condition of our problem. And then we write this nice drainage problem, which is a nice math trick, as I will show you in a second. And basically, so you write the lubrication equations. That's something that has been solved before is the fact that you can find a solution at the top. And then something that we have worked on is the fact that you can generalize this for the angle dependence. But the result is intriguing because the thickness varies with time. But what you see is that if time is large enough, essentially you can neglect the 1 in your square root here. And so if you cross the 1, you can take the hi square outside of the square root and you can cross it with this hi here. So the thickness no longer depends on the initial condition. So you go to something that is sort of universal. This is for Newtonian fluid. If you do the same thing for a random, arbitrary, viscosity, you have the integral of the viscosity. And I said a couple times already, but I'll show it now, that the viscosity is like a doomsday equation. And the doomsday equation, as we know, is almost constant and eventually goes to infinity. So if you do that, you can find the final thickness. So this final thickness is h sub f and depends on a number of things: the initial viscosity, the geometry, gravity, density, and mostly this curing time. Right? So when is it that this thing ceases to be a liquid and becomes an elastic? So this suggests that if I want to change the thickness, I have to change the polymer that I'm using. But this is forgetting that actually you can truncate this curve by mixing things and not injecting right away, right? And this is what we call the working time or procrastination time, right? So you mix, you wait, and then you push the bubble. And so that means that basically you can make your curing time appear shorter, so tau c minus tau w, and so you can make your thickness become larger. You cannot go the other way around. Okay, the bottom part, it's again the same equation as the pendant drop, but just in a bit of a weird geometry. You can find all kinds of shapes, but it so happens that we have a void fraction of 50% as we predicted before, and our dimensionless number between the radius and the capillary end in this case is more or less 1. So we tend to get these shapes. So that's the bottom. We have the top. You can match both, and if you match both, you get essentially this shape. So the green is the experiment, the red is the theory, so it works fairly well. And then we have this plot, which appears boring, but is very important. So the plot shows the thickness at the top as a function of the position in the tube. So that's a different tube. It's a very long tube, 1 meter. And what you see is that the thickness is actually 100 microns, plus or minus a few microns, and it's very uniform. And this is done without any fancy equipment. You just have to push with a syringe by hand. As long as you go far enough, you get this essentially for free. So it's a robust system. Then you can look at the elasticity. I'll go a little bit faster in the interest of time, but as I said, this part deforms more than the bottom, so you're storing excess length in the form of curvature. You can sort of, I really go fast, sorry, but I can convince yourself that the curvature of your actuator will basically depend on the applied pressure, the shear modulus, the geometry, and this HF here that comes from fluid dynamics. So you have a link between the fluid dynamics of the problem and the elasticity of the problem. You can test whether this formula is correct or not. So here we have a long hair, and that's about 40 centimeters or so, and you inflate it, so gravity matters in this case. So as it curves, it will curve more at the bottom than at the top, and as you increase the pressure, you increase the natural curvature if you want, and so you can integrate the Kirchhoff equations for elastic rods, and things are working well. Do the same in contact with something, you can do the same. That's inside water, so to suppress gravity. So if you have uniform curvature, essentially you're living on a sphere. And so if you have any random shape, you will form a small sphere that will close. And that's maybe the most interesting part, is that I can now change the thickness of my actuator by just changing the time at which I'm pushing the bubble. And so instead of pushing all at once, I'm going to push and stop and carry on. And so if I do that, I can change the thickness in each of these area. And now if I inflate this contraption with uniform pressure, I have a sequential actuation. And this is something that's called smart, because you give it a dumb signal, pressure increases, and you get an enriched dynamics, which is 1, 2, 3, 4. So I cannot do 1, 4, 2, 3, at least in this configuration, but you can go 1, 2, 3, 4. So it's a bit boring on the piano, but yeah, okay. I'm not a musician. Okay, yeah, and then we were asked, okay, can you do something special? So yeah, we can catch a bubble. So that's the same thing, right? So here we inflate this, and so the first thing that happens is that the gripper will grab the ball, and then the muscle will lift the ball. And as you decrease the pressure, the muscle goes down, and then eventually the ball comes back at the same place. Yeah, and then we can add membranes, and we can make cubes, and we can make sharks. And okay, yeah, it's reviewer number 3. Okay, I will go quickly, but just wanted to emphasize that we've done a number of similar-ish problems where we have wicking and capillary flows, where we can program these things to form interesting structures and shapes. We're also now looking at different fluids. So now this is more a foam, which is growing and inflating over time. I mean, this is the foam you buy when you do renovations at home. The shapes is very familiar. It looks a bit like a sessile droplets, but the scale is different for a number of reasons. It's not just exactly like interfacial fluid dynamics in this case, because if you let time evolve, you also have additional weird effects that are a bit like when you're making a souffle. So these are things that we're actively investigating, and this is due to the fact that you have a lot of things happening inside your structures in terms of the aging of the foam and so on and so forth. But you can play nice games. So if you make a number of these foams meet in some places, you can quickly assemble very important shapes like a turtle. And yeah, it's fun. Okay, so what about 3D? Okay, yeah, I'll say a few things about that, because I think it's in line with the story I've told before. So one thing that I want to pursue is to stack instabilities basically on top of each other. So this is something we've done a few years ago already, where we're moving this coating of glass in the form of a cylinder. And so what we obtain is this shape, but it's not very easy to photograph glass. So I'll show you the CT scan. Essentially, this shape is a non-woven texture made of glass, and a number of very intriguing problems for fluid dynamics. First, how much these things are fusing together. Second, what is the pattern selection, and then third, what is essentially the overall mechanical response of this type of material. So this is something I will be working on in the next few years. I think I've said that. And another intriguing theme that we are starting to explore, actually already for a few years now, but I would like to keep pushing, is this idea, right? So we know, and I think again you have to live in the rock for ignoring the idea that people are looking very actively at active matter. And so I'm not going to explain what active matter is, but I'm more interested into this. And so the question is, how is it that active matter or active material can build structures, right? So for example, the thermites, they manage to assemble these very nice structures without having basically a global architect that lays down a plan, right? So it's a bit like pattern formation, but now with active objects. And okay, so this is what we call multi-agent building, right? So you have for the thermites, but you also have, of course, in the case of bees and honey and everything. But I'm not a biologist, and I don't want to have bees in my lab. So these are the bees we have. So these are called hex bugs. I'm sure you may have heard of them. They are just eccentric motors that vibrate, and they have little legs that look a bit like a toothbrush. And if you put them on the surface, they will start to walk around and wander. They're not diffusive, but they're not ballistic either, right? So they make some turns. They're advertised as toys for kids and cats. Kids find them boring after 5 minutes. Apparently, cats like them for a long time. So if you have a cat, that's a good investment. If you have a kid, well, it's not expensive. So, buy a cat. And a cat. Buy a cat, exactly. Okay, and by the way, this is the orange stuff. And what we do is that we actually print these colors, and we bind 2 of them with elastic beams. And so you load an elastic beam. If the beam is thin enough, it buckles. They align in the same direction, and then they become more or less ballistic, and they advance. But they have a bumper, and they can interact with the environment with this bumper. So if they're alone, they're not very clever. If the goal is to go here, this guy will go. It will take a very long time. But now if they're together, they can actually solve complex problems. Not really, but they happen to actually navigate the maze. They implement what is called the wall following algorithm. So if you're ever in a maze, you follow one wall and you can solve the maze. So that's something that we've done and published, and it's a fun problem for people who like to worry about elastic rods. But now the new thing that we're looking at is that how they evolve into granular material, right? So now they're moving into this forest of granular structures, and they manage to, those ones manage to coagulate essentially these things. So you can revisit some classic problems of coagulations that will tell you that the number of granular material will actually decrease exponentially initially as a function of time. And we have improved now theory, I mean, this now published, it's not on archive, but that predict basically what is this plateau. But what we want to do, or what I want to do, is going back to the theme of kids. You have these things where you say link the number 1, 2, 3, 4, 5, and so the kid draws, and eventually you get a fish. Right? And so the question is, how can we sort of subtly direct now these robotic assemblies to, instead of making these, actually they look, the aspect ratio tends to be around 2 of these structures, but instead of making these things semi-randomly, how can we direct them to, assemble something that is, let's say, a fish, right? Okay, I don't know. That's what we're doing next. All right, so that's it for me. I just wanted to emphasize that this is work, of course, that was done by many people throughout the last 7 or 8 years. Some of them are familiar faces, like Joël, a long time ago, that you know, or Etienne Jean-Puyer, but yeah, and many very nice grad students who have been working on these things. And yeah, thank you for your attention.
Merci Pierre-Thomas. Est-ce que vous avez des questions? Le micro marche? On ne sait pas. Si, parfait. Oui.
En français, quand tu as ton tapis avec des poils de hauteur différente, ah oui, tu viens en contact, du coup ça fait penser à un séminaire qu'on a vu récemment, mais ça n'avait rien à voir, mais sur contact frottant, et enfin du coup je sais pas, ça me faisait, où il considérait ses aspérités élastiques, mais ça flambait pas, hein, mais du coup enfin je sais pas, est-ce qu'il y a tu vois un lien avec une mise en contact?
Oui, il y a des gens qui,
ouais.
en fait, là, en tribologie et en rhéologie, il y a des gens qui regardent aussi ces problèmes de contact en considérant l'hétérogénéité des structures. Donc il y a des liens de ce côté-là, je pense.
Juste indenté, t'as pas...
Alors on a peint aussi, mais ça c'est avant en fait. Donc on a travaillé sur ça aussi quand les poils étaient des forêts de nanotubes de carbone. Avec une peinture qui était une solution à base d'argent pour venir en fait faire des tampons for printing purposes. Et on retrouve des choses un peu identiques. Et là, parce qu'une question moi qui me taraude, c'est si j'ai ça, et ça rejoint un peu ce que m'a montré Basile ce matin, en fait pour venir déposer un liquide, si j'appuie maintenant sur ces structures-là et que certaines flambent, etc., combien de liquide je vais faire sortir de mon pinceau. Mais bon, ça fait plusieurs années que je trouve pas. Mais pour le coup, moi, un truc qui nous intéresse pas mal, c'est l'idée de regarder ça pour vraiment des senseurs robotiques, de robotique molle, en disant, donc, quel réseau, on va dire, neuronal je dois avoir pour transformer le nombre de contacts en une information sur la force? Quelle est l'architecture optimale pour... est-ce que je dois en mettre des grands poils à certains endroits, des petits poils? On regarde ça un peu plus dans ce contexte-là.
Moi, j'avais une question sur la manique où tu fais des plots dans une centrifugeuse à 3000 tours minute. Tu trouves que c'est non axisymétrique? Est-ce que c'est à cause de la force de Coriolis dans ce cas-là qui devient significative ou est-ce qu'elle est toujours négligeable?
Non, c'est négligeable. C'est des problèmes de délamination. C'est des choses que des gens connaissent assez bien. Quand ils regardent si on prend une colle entre deux plaques et qu'on la tire et qu'on l'étend trop, en fait, il y a des... Corrado, non? Tu peux travailler sur ça? Il y a des instabilités quand on prend une colle entre deux plaques et qu'on les tire, en fait, il y a des problèmes d'axissymétrie de ce côté-là. Et il n'y a pas de drag non plus de l'air. C'est souvent aussi notre question. En fait, même si on tourne assez vite, on peut faire un calcul de la corde à sauter et on voit qu'en fait, l'air ne compte pas, quoi.
I had a question about the tubular asymmetric actuators. So you presented the thing with 4 fingers that start moving at different times or different pressures, I guess.
Same pressure, different times. Well, yeah, okay. They all move at the same time, but with a different magnitude. Yeah.
Okay,
So it's not
it seemed they were moving one after the other.
So if they were hanging,
Yeah.
they would move one after the other
Yeah.
because you would have sequential bifurcations.
Yeah.
They're not hanging. Well, in their case, gravity is not important, so it's not a true bifurcation. So they all move, but that's slightly different, following the curves of different amplitudes.
Okay.
Well, it's the same, but it's...
And in the final
not...
state, they look all with similar shapes.
Oh, because they are coming to contact. Right?
Ah, okay.
They are the curvature, they have self-contact, so I think it's...
Okay.
Yeah.
And can you control the direction in which so could you have one that turns downwards and the other that turns upwards or left or right by turning your device?
So yes, we've done that. It's a bit cumbersome. So one thing that we've done is that you form this tubular structure in a mold, and when you're at the dilation point, you rotate the mold. So the mold is made in such a way that it can be rotated with respect to some other part. And now when you inflate, you go in different directions. It turns out you don't really need that, because if you think about the degree of freedom you have in the plane, basically, if you think about your triad vector of curvature, you can replace this direction by just curvature in the plane initially. And I can tell you one more thing, is that if you use UV light to control curing, instead of doing 1, 2, 3, 4, you can do arbitrary sequences of, but okay, we haven't done any of that.
Est-ce qu'il y a une dernière question? Je voulais juste savoir, dans la première expérience, les gouttelettes se repoussent, on n'a pas d'effet Cheerio. Qu'est-ce qu'il faudrait faire pour l'avoir?
C'est immergé, hein. Il n'y a rien à la...
Ah, ok.
C'est pas... Non, mais c'est... Bon.
D'accord.
pas
Les gouttelettes
la
sont
première fois
dedans.
qu'on pose cette question, mais c'est immergé. Ouais.
Ok.
Contrairement à quand vous aviez fait le truc de...
Eh bien, merci beaucoup.